Okay. Thank you for being here for this presentation. I'd like to start off by introducing myself. My name is Tiejun Chen. I am from VMware Octo, the office of the CTO. In this build, I belong to one group called as ATG. That's the Advanced Technology Group. We focus on impactful near-term co-innovation through better alignment and collaboration with our R&D product team, even our customers and our technology partners. Basically, we're trying to incubate emerging technologies with the goal of building differentiated technology solutions and augmenting existing solutions. Especially for me, my areas of interest are wide, like virtualization, hypervisor, container, WebAssembly, and edge computing, machine learning, AI, smart NIC, DPU. I've been working on a variety of projects or exploration on them. Okay, that's it. Okay, glad to make this talk. Back here, today I'm gonna talk something about machine learning AI on RISC-V. That's here, empower upstream machine learning frameworks on RISC-V. Okay, let's go through today's agenda. First of all, I'd like to give a very brief introduction of ML AI for this talk and jump to machine learning AI on RISC-V, especially what are those problems of running machine learning AI on RISC-V. After that, I will help you walk through our solution and such a landscape. Okay. Talking about machine learning AI, Just let's start from that trend of digital transformation. Nowadays, everyone is talking about digital transformation trend, shaping the future and even present day of our business. The key is data. Now, data is the essential driver to this exciting trend. Here comes the role of AI and ML. AI ML, short for artificial intelligence, AI, and machine learning, ML, represents an important evolution in data processing and computer science. A general methods and algorithms that are able to simulate our intelligence or human intelligence. Machine learning actually is a subset of AI. AI has the potential to transform all aspects of our business by helping them achieve measurable outcome. So AI workload is one of popular workloads in the cloud. We are cloud infrastructure. Most cloud providers provide a wide range of AI services that developers can make use of in their application. Obviously, AI is helping accelerate cloud growth. In the meantime, on the edge, I believe you very probably have heard of edge computing. Edge computing also has been evolved to run AI and ML on the edge, where a massive amount of data will be generated but needed to be processed in the real time for many reasons or just no benefits. Anyway, AI workload is the top one workload on the edge computing. This is why we have that important term, edge AI. So I would say AI, ML adopted everywhere from cloud to edge. What about ML AI platform? Typically, we are being accustomed to use some special hardware accelerators like GPU, FPGA, TPU to make AI ML. But sometimes we also can leverage CPU to make AI ML similarly with viable performance. In order to support this AI accelerator and a particular AI workload, we need some specific software like CUDA, OpenCL, and those machine learning upstream frameworks such as Tensorflow, Pytorch, and so on, and some other management and orchestration frameworks suitable for AI and ML computing, like that K-serve and MLflow, etc. Okay, now let's look back on RISC-V. In high level, we know and believe RISC-V is great and has a great future. As reported, there are more than 10 billion RISC-V calls already shipped and growing. It's really great. In particular, RISC-V has gotten noticed from communities of IoT, embedded system, and even data centers now, almost every domain. So AI ML is one of the very important workloads everyone definitely we need to consider how to fit ML AI to RISC-V. But indeed, you also can find some existing discussion or early implementation of RISC-V based accelerator by introducing sort of vector extension on RISC-V to make this mostly. Looks like everything is good, but what's the truth and what are the problem? The RISC-V was designed to handle the latest workload, including AI, machine learning, HPC, and most people thought. But actually, you can easily imagine something of still challenge RISC-V in the real world, right? Here, let's focus on those problems, machine learning AI. I'd like to categorize our machine learning usage into two different cases for RISC-V. One is that straightforward. Most hardware vendors intended to build such a RISC-V-based accelerator. In this case, probably they are targeted to leverage something their own vector or their own tensor implementation now. But the truth is that you just can find a very few RISC-V-based implementation on AI from cloud to edge, and mostly just for the machine inference. And you also probably have to do something else to use them, like you have to recompile your model. In other words, there are some additional efforts here, right? Other case, by contrast, what about deploy those popular AI hardware accelerators? I mean, a GPU, FPGA, TPU, or whatever on RISC-V-based host platform. Even in this case, RISC-V also meets many challenges. We probably miss those basic libraries for machine learning pre or post processing. Besides, those AI hardware vendors do not provide all necessary components of running their AI accelerators on RISC-V host, firmware, drivers, utilities, Tensorflow, Pytorch. More important, the vendor seem not have the official plan or roadmap to enable this thing to RISC-V, right? Even back to RISC-V vendor, only a few hardware featured with a PCIe bus, which is used to connect with those popular AI accelerators, typically. So I have to say, it's very hard to bring machine learning AI around RISC-V, and the conditions of extremely uncertainty from hardware to software. But when RISC-V is growing rapidly, we shouldn't wait. Instead, we should consider how we can tackle this problem to accelerate RISC-V adoption from cloud to edge. But what could I do now? Okay, to fast bring AI ability to RISC-V ecosystem, here I'm trying to explore a new way. Basically, I think we can expose accessible machine learning framework to a local RISC-V target. What I'm saying here is wherever you put your RISC-V, in most cases, your RISC-V can access to other ARCs, x86, ARM64, PowerPC, based host platform, in which the platform have AI abilities powered by any AI accelerator or just some powerful CPU code. Never mind. We can leverage them to empower native AI machine learning usage on RISC-V in our web way. If so, I think that would be awesome, right? Okay, let's move on to take a close look at how we make this happen. Let's simply put this first. In our solution, we are deploying sort of lightweight ML upstream frameworks on RISC-V targets, while deploy fully machine learning upstream frameworks on accessible other ARC-based platform. We are using transparent procedure code to expose those remote Python-based machine learning frameworks module to a local machine learning frameworks on RISC-V. Here, one should be mentioned is on local RISC-V, we just set our machine learning upstream frameworks composed of only necessary Python module interfaces, not a fully machine learning framework. I think I need to elaborate a bit. So when you run your AI application written with those native machine learning upstream frameworks, Tensorflow, Pytorch, what's going to happen with my solution? We will prepackage some necessary machine learning frameworks, just including a few Python module interfaces. For example, in the case of TensorFlow for machine learning inference, typically we need a few key APIs essentially, like model load to load your pre-trained model, then call another API predict to do a machine inference with your your data. I just need these two Python API. Not only we don't need to do that for some reason, like low memory overhead, footprint, security, etc. Most important, you remember that these frameworks do not support RISC-V at all, as I mentioned at the beginning, right? Even worse, it is almost not possible to compare these machine learning frameworks by yourself or to deploy them on RISC-V and nowadays. Okay. Right here, the backend agent will be deployed running on local RISC-V as well. On the host, you should have any machine learning frameworks on your host platform accessible to your RISC-V. I'm sure this always true in any cases. Any machine learning frameworks and any AI accelerators. We also deploy our host agent response to a remote Python procedure module call. When you run your AI application on our kind of live machine learning frameworks on RISC-V, that local agent will automatically request remote host agent to expose the remote corresponding Python module back to us to perform your AI application. That's sort of that bridge. Furthermore, we'd like to boost machine learning performance. And now, this performance is also very important for your real AI case. Here we introduce some graph compiler like NVIDIA TensorRT, Intel OpenVINO, TVM. Basically, this graph compiler. The purpose of this graph compiler is to optimize the processing of forward and backward pass over the computation graph. The compiler perform optimization at several levels. Anyway, we enable them as such an automatic backend software acceleration. Our unique mechanism can intercept Python code to pass your model and compile and further optimize your model to make a better performance on your underlying AI accelerator. When your AI application call predict to machine learning inference, they also can intercept that predict API to use that pre-compiled intermediate representation to do real machine learning inference and get the result back to your request. Okay, now I can say our software stack seamlessly integrated with the standard deep learning development environments with the ability to deploy flexibly on RISC-V platform and further optimize model once boost machine learning performance. Although I already introduced our solution, but I'd like to quickly sum the whole approach up well to help you understand the essence of our solution. So basically, our approach consists of three parts. The first one is accessible host that will offer real AI ability with AI accelerator, GPU, FPGA, TPU, or whatever, or even its own CPU code somehow. We just enable our server agent to help attach the ability to our local RISC-V targets in fact. The second one is on your RISC-V target with our client agent. It helps for fetching AI ability from your accessible host. Even some helpers also can be exposed from machine learning frameworks on accessible hosts, like here. I'll give you one example. That's about pre-processing input from TensorFlow. Usually we use this pre-process your images as an input to your model, right? Actually, we can extend this to other necessary components if RISC-V does maybe something like OpenCV. We also can expose them in the same way. Okay, then we on AI execution output info, it can perform very well locally. Third, the last one is the backend graph compiler acceleration. The goal of introducing this is to, on the one hand, you can get the best performance for your AI accelerator. On the other hand, this also implies that this can help support a variety of hardware accelerators flexibly. One thing is what they are mentioning here is there's no any code change for your AI application running native upstream versioning frameworks. This is a real cool feature I love in my solution. Okay. Now I believe you can understand what I'm doing here with this solution. Just let me show some demo to help you get more direct insights on this. Here I have two demos. One is to empower AI ability from x86 with GPU to RISC-V. The other is similar, but from ARM64 to my RISC-V. Let's get started. At first, this is one x86 based PC. You can check some configuration information on ARC, IP address. Actually, in this PC, I have one NVIDIA GPU card installed, as you see here. Okay. Here is my RISC-V target. Let's also check something. ARC IP addresses. Okay. I'm going to run one simple TensorFlow-based Python program. Here you can find all code. Nothing is related to our solution. I mean, we don't introduce anything to your native AI code. Right? Just let's run this. Yeah, you can find we run this on RISC-V over TensorFlow, but that GPU can't. Cool. Next, I will show another example. This time, the host is an ARM64-based platform. Again, I will show some information about this platform, like IP address, even that accelerated tensor core. Actually, this is one NVIDIA Jetson TX2 platform. Okay, I will run another simple TensorFlow code after check this RISC-V configuration like before. Let's see that code. Yeah, as you see, it's also another native. Yeah. Okay. It still can work on very well with that TensorFlow and that tensor core from my ARM64 based Jetson board. Okay. This is to a demo. Now as a summary here with my solution, the essence is to empower native AI ability over native machine learning upstream frameworks on RISC-V by means of accessible hosts with any accelerator. Especially, it can fast support any machine learning frameworks you need or just you like on your RISC-V. You also can power AI easily on RISC-V. I mean, you can dynamically install any accelerator on your host if needed to be in your case. And based on this design, you can deploy more accessible acceleration hosts to make them available for your RISC-V. You also can think of more on this solution, like we can extend this solution to any non-standard Python-based machine learning frameworks, or expect for Python, expect for TensorFlow, Pytorch, as I'm showed here. Actually, there are some other specific Python machine learning software. In the case, can work. Even you can deploy framework A on RISC-V, but deploy B on accessible host. So anyway, this implementation can help us bring RISC-V powered by AI ability into more use cases and more areas from cloud to edge. In the end, let us further imagine a bit more. For me, I believe one day we will have RISC-V based AI accelerators supported very well by the hardware vendor and the community. Actually, nobody does this right. But at that time, do we still need this? I think this still would be valuable. Just think about something. Another low-end RISC-V platform, right? And even we can expose RISC-V acceleration to other arcs if they also need AI ability, right? Okay. Furthermore, I think the next generation hardware platform or infrastructure will be heterogeneous. x86, ARM, RISC-V should be adopted simultaneously due to any reason. Maybe just a new business model or good technical requirements, whatever. These different arcs will coexist and will be working together somehow. Some potential good cases are like DPU, data processor unit, SmartNIC, or thoughtful HPC. So these solutions still can play a very important role, as I believe. In addition, we could introduce a WebAssembly to build such a universal machine learning binary enabled with this way to deploy one AI workload on any platform. And it also can easily be migrated. But that's another attractive story, and I'd like to talk next time. Okay. That's all I want you to talk today. Thank you for your time. And I'm sorry I cannot attend our great summit this year in person. But if you have any questions and comments on this, please reach out to me via my email address or Twitter. I'm happy to address them offline. Thanks.